Alright, I have some totally sweet stuff for you today. What we're doing today is an introduction to something called a parametrically defined function. And this is really going to expand your sense of what a function is and a sense of what math can do. We're going to sort of start breaking some of the cardinal rules of things that we had done before. And we're not really breaking them, we're just sort of defining things in a different way so that we can just work with more awesome things. So the first thing you need to recall is you need to recall that the key idea behind a function is that for each input value, we will have at most one output value. And the reality is, as soon as I say input value, I would bet that your brains latch onto the idea that, oh yeah, that input value is supposed to be x. And the output value, yeah, that's supposed to be y. Right? And so that, my note in red here is more than likely your mathematical history has shown you only one type of function. And that function is where y is a function of x, right? And what that means is, for us, x is always our input, and y is always our output. And that's sort of always what it is. You may be aware, when we do an inverse, if it's a one-to-one function, then now y is the input and x is the output, and ooh, cool. But the idea is x and y are always directly tied to one another, and that changes in parametrically defined functions. So with a parametrically defined function, what happens is our independent variable, our input variable, is going to be a parameter. And that means it's something like time. And our x and y and even z variables will depend on that parameter. So what that means is when we have a parametrically defined function, we're going to have things like, okay, x will be equal to t squared minus 1, and y might be equal to the sine of t. And so the idea is it's not like you're plugging in x and getting back y. You're actually plugging in t and getting back x and y. And some people are like, whoa, that's not fair. When we input something to a function, we're supposed to get one output. And I would agree, and this is going to sound like cheating. When I plug in t, I do get one output. That output is the point x comma y. I'll admit it has two components to it, but the reality is I can think about those things together, right? And what's sort of exciting about that is we can break the vertical line test now, right? The reason we have the vertical line test, and I'm not supposed to take too much time with this, I told myself not to, but here I go. When we have a function like this, we would say, oh, this is a function because it passes the vertical line test. More precisely, this is y as a function of x, right? Now I can take something like this and say that is a function. It is a parametrically defined function. X is some crazy function of t, y is some other crazy function of t, and what was important is that, as my finger traced this path, my finger was only in one place at any given time. My finger was here at time 0, here at time 1, here at time 2, 3, 4, 5, 6, 7, 8, 9, 10. Like, for any given time that I were to plug in or evaluate for, there would only be one point. That's what a parametrically defined function is. I have a couple of examples that I want to look at, so let's get right into those. Okay, so for this example, I'm asking us to consider the parametrically defined function given below. So notice that I'm giving you sort of x as a function of t and y as a function of t. I want us to complete this table and then use it to sketch a graph of the function. And in that graph of the function, I want us to include the orientation of the curve. In other words, what direction is the curve going? And then that's weird because for us, curves have always been, here it is, it's the graph of x squared. But in this problem, time is moving along, and we want to know where does this graph, where is it going, in what direction is it proceeding, right? So I'll go through a few of these blanks together, and then I'll leave some of them to you to do. So first of all, what does this over here mean? Well, this means when you plug the time of -2 into these things, you should get outputs of 13 for x and -3 for y, right? This next sort of column means, well, when I plug -1 in for time in x, I'm supposed to get back 6. So for this value here, all I really need to do is take -1 and evaluate the y expression for it, right? So if I just do y equals 2 times -1 plus 1, that'll be -1, so I get -1, right? Keep in mind, over here for notation, I could have said, y of -1, just to sort of make that more clear. Sorry for the jumbled writing there. We could write y of -1 to indicate, hey, I evaluated at -1. Right? So the next one over is when we're working with 0. So when I do x of 0, I get -2 squared minus 3, which is 1. Right? When I do y of 0, I end up with 1, so we can put in 1 there. So I just realized that I have sort of a mistake in the setup of my problem. This 5 here needs to be a 3. So sort of change that before we move on to the next step. The next thing we need to do is we need to figure out what that top value of time is going to be. So in order to do that, we are going to use our x and y values and sort of solve for time instead. Right? So in order to do that, I'll start with x first. Right? So if I set -2 equal to t minus 2 squared minus 3, right, we'll have 1 equals t minus 2 squared. When I take the square root of both sides, I'll end up with plus or minus 1 equals t minus 2. It sort of ends up leading me to the idea that time could be 1 or 3. And what that means is, it means that there are effectively 2 times at which the x-coordinate is -2. That's frustrating for us, because it's hard for us to tell what this is supposed to be. I mean, 1 and 3 are both between 0 and 4, so either one of them is fair game. The only way we're going to be able to figure it out is to use the y-coordinate, right? So if I set my y equal to 3, so 3 equals 2t plus 1, if I'm solving this, I'll end up with effectively finding that time is 1. So there were 2 times that the x-coordinate was -2, but only 1 time where the y-coordinate was 3. Those things both match up with time being 1, and that tells us that the time at which this occurred must certainly have been 1. Right? So the last thing we need to do is sort of follow through on this last part in terms of figuring out what the time and the x values are for the last one. So if you haven't already done so, pause the video, work through those last 2 things, and then we'll talk about those. So I'm going to sort of shift us sideways a little bit. So for this section, we know that the y value has to be 11. Let's see, I need to use some other color. Purple sounds good. So I'll set my y component equal to 11. 11 equals 2t plus 1. Solving that out, we're going to end up finding out that time is 5. Right? So we know that the time that this happens is 5. And that's frustrating. Finding out that that was 5 just made me aware of the fact that this is also a mistake. That value should have been 9. I'm sorry, this problem isn't working out as pretty as I wanted it to, but hopefully you'll forgive me. So we found out the time was 5. If I take that time value and substitute it back into x, I'll end up figuring out that my x-coordinate is supposed to be 5 minus 2 squared minus 3. So this is, let's see here, 9 minus 3, which is 6. So there's my x component. Right? I now have this entire table filled out, right? And the problem had asked us to graph this thing and indicate our orientation in the process, right? So I want the orientation of the curve as I'm working through this thing. So I wonder if I can remove some of this work so I have some space to work with. Yeah, that'll have to do. So I'll sort of work with my graph in this space here, and this graph doesn't need to be perfect. I just want us to see where it's coming from. So the first point I have there with time being -2, we have an x-coordinate of 13 and a y-coordinate of -3. So you sort of got a point here, right? And it's almost tempting to put a little -2 there to indicate, like, hey, this is what was happening at time -2. So then we had a point at 6, -1. So 6, -1, right? Then, so that was at time -1. Then we had this point at 1, 1, so we've sort of got a point here-ish. Then we had our point at -2, 3, so then you sort of got a point about there. We had a point at 1, 9, so we've got way up here or so. And then 6, 11, we're sort of coming back to here. And remember, we had times for these things. This was time 1, this was time 4, this was time 5. And so we sort of have this sense that this curve is doing something like this, like it's going in this direction, and it may have some sort of rough parabolic path. That's what it looks like to graph a parametric function by hand. It's not it's not a quick process, but what I wanted here was to sort of give us a sense of how these parametric functions are constructed. That x and y both depend on t, and that once we have those values, we can plot them out, and moreover, we can actually see where the point is, like over a period of time, where this function is going. I know the last example was really long. I'm hoping this one's going to be faster. So the graph of the parametrically defined function given below, which is x equals cosine t and y equals cosine t times sine t, is shaped like the symbol for infinity. And to be honest, like maybe that's enough to sort of mentally bring you back in. You're like, whoa, I can, you can tell yourself, I can graph infinity now. This parametrically defined function looks like what I just drew, right? And I've got a couple questions for us. So part A. What point on this curve corresponds to time being 0? And that should be an easy thing to do. But pause the video for a minute. Think about how you would do that. Like, effectively find the point that corresponds to time being 0. So, in order to do that, all we really need to do is evaluate both x and y for t being 0. So, x is going to be the cosine of 0, which is 1. And y will be the cosine of 0 times the sine of 0, which is 0. Right? So the point 1, 0 is where time is 0. So I'm effectively saying that this point right here is where time is 0. And the reason that's significant is that's where the curve quote-unquote starts. Really, there's nothing wrong with t being negative, but t equals 0 is a nice way to think about, hey, the curve starts that way. Rather, starts there. Now part B is asking for us to determine the orientation of the curve. In other words, which way is this curve going? Does it go the way that I drew it, where it goes this way, or does it start out going downward and going back this way? How can we figure that out? And I want you to, pause the video for a second, think about that and process, how could we figure out which way this curve's going? And I hope the thought that you came up with is, we could just take a value of t that's greater than 0 and see what happens, right? And some of you may have gone so far as to actually plug in like pi over 4. If we were to plug in pi over 4, so when time is pi over 4, we would get an x-coordinate, that's the cosine of pi over 4, which is root 2 over 2, and a y-coordinate, which is the square root of 2 over 2 times the square root of 2 over 2, which is, 2 over 4, which is 1/2. And the sense that we have there is, wait a minute, both the x and the y coordinates are positive, so we're looking at, like, that point is probably there, that one there. This is where time is pi over 4. And that sort of gives us confirmation that, oh, the graph is clearly going in this direction. And that means that the orientation of the curve will continue to sort of follow that pathing all the way around the thing until I get back to this to the starting point again. And then the idea is this curve is basically just going to keep drawing out the infinity symbol forever, right? And it's sort of like, whoa, like infinity inception, right? You've got this idea that, as time goes on towards infinity, this infinity curve is going to be drawn over and over and over and over and over again. So the final question that I want us to process then is, what is the smallest positive value of t where the curve returns to its starting point? In other words, what's the smallest value of t where we're going to get back to that initial point? So pause the video, figure that out, like solve that, and come back and we'll talk about it. Right? So the idea is we want to know when we get back to this point, when we get back to the point 1, 0. Well, if we take our x and y, function pieces, expressions, and set them equal to those, we should be able to find out. It turns out that we would need to have 1 equal to the cosine of t, and we would need 0 to be equal to the cosine of t times the sine of t. If I solve both of these equations, I'll end up getting here that, so where's cosine 1? Well, that happens at 0, and then at 2 pi, and then at 4 pi, and so on forever. For the other one, 0 will be equal to this when either cosine or sine is equal to 0, so it happens more often. This will be at time 0, at time pi, so I missed, it'll be 0, it'll be 0 at pi over 2, at pi, at 3 pi over 2, at 2 pi, sort of, every pi over 2 radians we're going to have this happen again. So the question is, what's the answer? Right, what's the smallest value of t where we get back to that point, right? Well, the only time we get back to the point to both x and y being there, this seems to happen at 0, and then for as much as there's lots of values here, both of them happen again at 2 pi. So the answer for part C is that the time will be 2 pi. it takes, a time of 2 pi for this graph to sort of complete one complete loop of itself and then begin to repeat itself. I know this video is longer than I wanted it to be, but I hope that this introduction to parametric functions is exciting, that we have the sense that like we can do a lot more things now. We don't have to follow the vertical line test, and that opens the floodgates for lots of crazy things to happen, but we're unlocking the potential of mathematics to do awesome things. So I will see you in the next video.